we should really take a couple minutes and talk about something that kind of unifies all the whole gas chapter together, and that is kinetic molecular theory. Now, a long, long time ago, when scientists started studying gases, they needed to start with a set of rules that described what gases were and how they behaved, so that they can kind of compare one sample to another. Now, a lot of what we're about to talk about, we might not today agree with, and that's actually pretty important, because it's going to give us a whole new set of ideas that'll help us explain other and new great phenomena. More on that in just a minute. Let's figure out these 5 basic rules that describe kinetic molecular theory. First of all, that gas particles have 0 volume. That quite literally means 0. Gas particles are matter. We know that matter is anything that has mass and takes up space. So to say that it could have 0 volume already is a statement of untruth. But to scientists working back when gases were first discovered, this was an important rule. Second, gas particles are in constant straight-lined motion. I think that honestly that this is pretty much agreeable by everybody, that the gas particles are constantly moving. They'll tend to move in a straight line until they bump into something, and then they'll change that straight line into a bendy line, I guess. Collisions with the container are elastic. Now, I bolded the word elastic there to try and make sure that you understand what elastic means. Elastic means that if you bounce off of anything, off of another particle, off of the wall of a container, that you will bounce off with exactly the same amount of energy that you bounced in with. Now, that is a statement of non-truth. Anytime that an object bounces into another object, it's inherently going to lose a little bit of energy, whether it's through giving some of its energy into the other object through like momentum change, or if it's going to be losing it through friction. There's always a loss of energy. It's impossible for those collisions to be completely elastic. Next one is that gas particles have absolutely 0 attraction or repulsion, either for each other or for the container. And that also is a statement of untruth. We learned way back when we started learning about the different types of bonds, whether it be ionic or mostly covalent, that atoms are going to be held together by different forces, and we can't stop that. Even molecules, after the bonds are made with covalent bonds, are held together through intermolecular forces. Those are attractive forces. Even nonpolar molecules, ones that have the electrons completely shared equally around the outside of their structure, have an attractive jello-jiggler style force called London dispersion forces. So to say that gas particles are not allowed to attract or repel one another, again, is kind of a statement of untruth. But it had to be back then. And then finally, gas particles at the same temperature will have the same kinetic energy. Now this we can actually agree with. Temperature is defined as the average kinetic energy of the particles in a substance, so kinetic energy and temperature should go hand in hand. Now, of these 5 ideas that were laid down way long time ago, of kinetic molecular theory, we can't agree with 3 of them, which means we only agree with 2. Now you're probably wondering, well, if all of these things aren't true, then why are we learning about it? And honestly, everything is kind of building to this next image that I want to show you. We're going to go back to the particles in a box. And let's set those particles off in motion. And while these particles are kind of moving, notice that, yes, they're moving in a straight line pattern until they're acted on by another force. Now I'm going to add some ice to this image. We're going to start to cool the sample down. Notice what's happening to the molecular motion. It's starting to slow even more. And as that temperature begins to drop ever so much more, take a look at what's happening to the particles. The particles are spending more time next to each other. They're having an attractive force. And look, that attractive force is becoming so great that, does this gas look like a gas anymore? I think it's a liquid. If it's a liquid, it can't be a gas, and therefore it can't obey any of our gas laws. Let's cool it even more, and notice now that even though the molecules had been slipping past one another, they're not doing that anymore. I think you've just seen the transition from liquid to solid. So again, if a gas isn't a gas anymore, it really can't obey the gas laws. So the gas laws really only work if the material is a gas. Now, the kinetic molecular theory puts all of these ideas out that basically tells us how a gas should behave under the perfect conditions. But we know that this isn't a perfect world, that we have more than just this one state of matter. So the kinetic molecular theory gives us something called, instead, an ideal gas, which is exactly where the ideal gas law got its name from. We would define an ideal gas as any gas that behaves according to the rules of KMT, or kinetic molecular theory, absolutely 100% of the time. That actually limits the conditions under which we can actually use the ideal gas law, or the combined gas law, or any other gas law for that matter. Because if you're not working with a gas, those gas laws fall apart. I just want to kind of reiterate that there are in fact 5 recognized states of matter. You might be familiar with 3 of them. Solids, liquids, and gases are ones that we usually teach to most people because they're the ones that we're going to come in contact with in an everyday life. Plasmas are kind of interesting. What I want you to imagine is that a plasma, if you can imagine the structure of an atom with the nucleus in the center and then the electron field around the outside, is if the gas particle starts moving so fast that the electron cloud almost can't keep up with the nucleus, and that the electron cloud starts to move away from the nucleus, separating itself, that you end up having an ocean of these disjointed electrons with these positive particles racing around at really top speeds inside of this electron soup. That's essentially what a plasma is. On the other side of the spectrum, we actually have a state of matter that's more solid than solid. It's called a Bose-Einstein condensate. And what I'd like you to imagine when you're dealing with a Bose-Einstein condensate is that the molecules, or I should say the atoms, are cooling and slowing down to such an extent that the molecular motion really starts to slow, and that the atoms, if you can kind of imagine the electron fields are like Velcro, and that the Velcro kind of gets stuck and it starts to collapse in upon itself. There's a lot of quantum mechanics involved in Bose-Einstein condensates, so if this is an area of interest, particularly quantum mechanics, you might want to take a look at the video that I've attached after this one. It'll actually explain in more depth what a Bose-Einstein condensate is. The same thing with a plasma. But let's back to the point here. Essentially, in this zone only, the gas laws will actually work. So under different sets of conditions, which we're going to call extreme conditions, the gas laws will fail to work. And this is all according to kinetic molecular theory. So there's a couple different ways that we can make a gas not a gas anymore. First of all, we can manipulate temperature. So if we reduce the temperature back enough, we'll slow the molecular motion down to the point where they will attract one another. Those intermolecular forces come back into play. And you could create a liquid or a solid, or, under really extreme conditions, a Bose-Einstein condensate. The other thing we can manipulate would be the pressure. I can actually take that same sample of a gas and increase the pressure. Now that would push the actual molecules or atoms closer and closer and closer together until we artificially create these other tighter states of matter, whether it be a liquid, a solid, or a Bose-Einstein condensate. On the other side of the extreme variety, I can take a gas and turn it into a plasma essentially only by making those molecules move faster. Now that will not happen by manipulating the pressure. So if I wanted them to move faster, I must manipulate only the temperature. And if I increase the temperature, I can effectively create a plasma. Again, check out the other videos that I have after this. I think it would really help you understand what a Bose-Einstein condensate is, or what a plasma is if you're interested.